Hi everyone, my name is Ben Oler. I'm the AFM Business Manager here at Asylum Research, an Oxford Instruments company. I'd like to welcome you to today's webinar. Our topic today is Contact Resonance Tools for AFM Nanomechanics. We're honored to have Dr. Donna Hurley joining us as co-presenter today, along with Dr. Roger Pruksch. Dr. Hurley leads the AFM Nanomechanics project in the Material Measurement Laboratory at the National Institute of Standards and Technology in Boulder, Colorado. Her project team has worked for more than 10 years developing contact resonance AFM techniques for quantitative nanomechanical imaging. Dr. Pruksch is president and co-founder of Asylum Research. He has been active in AFM development and research for more than 20 years. He is co-inventor on several patents in the field of AFM nanomechanical measurements. Contact resonance is just one of the capabilities in the Asylum Research NanomechPro toolkit, which offers a full suite of tools for characterizing nanomechanics, functional mechanics, and thermomechanics. The Asylum NanomechPro toolkit ensures that you always have the best tool in hand for a given measurement and enables you to compare multiple techniques for consistency. Please feel free to ask questions during the webinar. You'll see a text box in the webinar interface where you can enter these. We'll collect the questions, and Donna and Roger will answer as many of them as they can, as time allows, at the end of the presentation. If we're not able to answer all of them, we'll be sure to get back to you individually. Today's webinar is just one of many planned for the year. If you don't want to miss these, please go to our website, which is shown here, www.asylumresearch.com/webinars, and you can email us to subscribe to our mailings. Also note that the presentation today will be recorded and available for viewing later. Simply follow the same link that you were sent in the registration confirmation email, or again, you can go to the website that's again shown here. So let's go ahead and get started. Roger's going to be speaking first.
Thanks for the intro, Ben. Welcome, everyone. Thanks for listening in on our webinar. I want to start off by saying a little bit about what I could call our nanomechanical philosophy. The revolution that was started by Binnig and Rohrer with the invention of the STM, and then later Binnig, Quate, and Gerber's invention of the AFM, has changed the way we look at the world. In the case of mechanical measurements, our experimental laboratory has shrunk down from standard macroscopic techniques you may be familiar with to contact areas between the tip and the sample that are just a few nanometers on the side. We expect many of the physical properties of materials on this tiny length scale to be different from what they are in the macro world. Others may more or less stay the same. Unfortunately, our macroscopic intuition isn't always perfect in this new world, and at times we can fool ourselves. One way around this is to approach whatever problem you are trying to solve from more than one direction. That's exactly the motivation for the NanomechPro toolbox that Ben mentioned. We firmly believe that one tool does not fit all applications. Much like it is a good idea to avoid changing the tire on your car with the pliers, it can be done, but you will probably make mistakes, and you might even ruin your tire or the bolts along the way. The toolbox provides an array of techniques for making nanomechanical measurements. This ranges from AFM Modulus Measurements, in this example a spectra sample, simultaneous loss tangent and modulus measurements of this polymer sandwich, nanoindentation measurements of this low-K dielectric material, force curve modulus measurements of this live cell in solution, and finally the subject of today's webinar, this contact resonance stiffness image of a magnetic recording head, where the stiffness has been overlaid on top of the topography. This is a brief outline of the topics we'll discuss today. We're going to start out with a discussion of modulus measurements in general in AFM, so covering a few different techniques I alluded to briefly in the last slide. We will look at the measurement of moduli as a sort of a three-step approach where we look at acquiring the data, interpreting the response of the data in terms of some sort of stiffness parameter, and then actually getting to the modulus. Donna and I will both talk about different techniques for getting data, so different ways of measuring the contact resonance. We'll talk about a lot of applications and results, and also spend a little bit of time talking about uncertainties and artifacts in the measurements. I should also mention that If you're new to mechanics, or if you're new to nanomechanics, you may want to listen to our first webinar, which you can find on our website that Ben indicated. And that in particular involves a discussion about modulus and contact areas, which are important ideas for any kind of nanomechanical measurement, certainly for contact resonance. The elastic moduli of material interest to most AFM kinds of measurements range from maybe a kilopascal for very soft rubbers, gels, and so on, up to several hundred gigapascal for hard materials like diamond or hard ceramics. That's quite a few orders of magnitude, and it's quite challenging to cover all of that. And certainly with any one technique, it's basically not possible. Force curves, a very common technique, can cover a small range of that, maybe 2 to 3 orders of magnitude for a given cantilever stiffness. If you want to cover a large range, you have to use more than one cantilever. Force modulation is sort of similar. It covers maybe 2 to 3 orders of magnitude. AFM, because the cantilever essentially carries different spring constants with it, because AFM can use more than one higher resonant mode, it can cover a larger span of frequencies. Contact resonance, the topic of this webinar, is a contact technique where the cantilever is oscillated in contact with the surface. And again, depending on the stiffness of the cantilever, it typically covers a few orders of magnitude, 2, maybe 3. Nanoindentation is a technique where the cantilever, or not the cantilever, I'm sorry, the indenter probe is pushed into the sample vertically without any sliding motion. And again, you can cover several orders of magnitude with that technique. I should note that contact resonance, the subject of this webinar, is uniquely positioned to measure moduli on the stiff end of the range. So sort of from 1 gigapascal up to several hundred gigapascals. The techniques on this page are all part of the NanomechPro toolbox for modulus mapping. I should mention that 2 of the techniques, AFM and contact resonance, the subject of today's webinar, are examples of AC or resonance techniques. And one advantage of these techniques is that they allow you to measure the modulus and the dissipation or the loss modulus. So the elastic modulus and the loss modulus. The loss modulus is related to the energy dissipated by the material per cycle, per oscillation cycle, and can be related to as well to the loss tangent, as was discussed in our first nanomechanics webinar. Finally, in my first philosophy of AFM nanomechanics statement, I mentioned that it is nice to have multiple techniques that can be compared. Contact resonance and nanoindentation are unique in that they fit the bill here at that sort of high end of the modulus measurement range, the sort of 1 gigapascal to several hundred gigapascal range. So getting modulus measurements out of AFM experiments is kind of a universal problem independent of all those techniques. There's some very common things. I'm going to take the techniques on the previous page and break them up into a couple general categories. The first is what I'm calling deflection techniques, and that's where we measure the bending of the cantilever to get things like DC deflection, amplitudes, and so on. So techniques that use that are force curves, force modulation, indentation. You can also look at what I'll call resonant techniques, and that's things like contact resonance, AM/FM, and frequency modulation. Now, in each case, our first step is to measure an observable that's dependent on the stiffness. So in the case of deflection, it's the slope of the deflection versus distance curve for a force curve. In the case of resonance measurements, like contact resonance, it's the shift in the resonant frequency. Once we have that data, we can convert that observable to a stiffness in units of newtons per meter via some sort of model. Now, a lot of times we don't really think very much about what these models mean, but in the case of a deflection in a force curve, it's really Hooke's law, We're assuming that that the deflection of the cantilever is linearly proportional to the force on the tip of the cantilever linked by the spring constant of the cantilever. Now, often that's a very robust and good model. Sometimes, though, if the deflection is large, that may not be. It may be nonlinear. There may be some other effects that complicate that, things like friction and so on. Same thing with resonance. We need a relationship between the resonant shift and the stiffness. Now, all of the techniques then, once you have the stiffness, we have another step, another modeling step, and this is one where probably there's even more range of variation in how good the models are, and there's a lot of discussions in the literature and so on about different models. But there has to be some model that connects stiffness to the actual modulus in units of newtons per meter squared, whether it's the Hertz, the Snedden, Punch, JKR, DMT, and so on. Before we leave this slide, there are 3 general points I'd like to make. First one is that step 3 here, where we talk about the stiffness to modulus model using the Hertz, Snedden, Punch, JKR, all these different kinds of models that people talk about. While the NanomechPro toolbox has a lot of these things, and there's a ton of attention paid to these things, in many ways, this isn't the most important step. The most important step really is number 1, the step where we measure the observable, either in the case of a force curve or other deflection techniques, the deflection versus distance. In the case of contact resonance or AM/FM, the resonance shift. If this measurement is bad, if it's polluted, then everything downstream of it will also be polluted. Second point is that resonance is an attractive observable in many cases, since we know that the fundamental precision of a frequency measurement can be extremely high. It's easier to count pulses than it is to measure a voltage level. And in fact, one way to increase the precision of a voltage level measurement is to convert it into a frequency measurement. The third point is that resonance techniques provide, and I mentioned this before, provide a pathway to also making dissipation and loss measurements, so loss moduli measurements, for example. That is much less obvious in deflection techniques. In the next slide, Donna Hurley will introduce you to contact resonance measurements.
Thanks, Roger. Before I get started, I'd like to make some acknowledgments. First, I'd like to acknowledge my NIST coworkers here in beautiful Boulder, Colorado. Jason Kilgore, Tony Koss, and Ryan Tung are all essential to our contact resonance project. I also want to acknowledge our collaborators in many places, some of whom are listed here. Finally, I'd like to thank Asylum Research for inviting me to participate in this webinar. If you only remember one thing about this talk, I hope it's this slide, because it captures the key concepts of contact resonance, or CR. We can think about contact resonance using the familiar force displacement curve in the upper left, as well as the finite element simulations of cantilever vibration on the right. When the tip is out of contact in free space, we're on the right of the force displacement curve. And the cantilever has a preferred or natural resonant frequency, here 11 kilohertz. When we bring the tip into contact with the sample at an applied static force, we're now over to the left on the force displacement curve. Here, the resonant frequency increases due to the elastic coupling between the tip and the sample. In this case, the resonant frequency is 52 kilohertz. Now, contact resonance is all about exploiting these frequency changes to extract information about the sample's mechanical properties. As a final note, I'd like to point out that in contact resonance, the high-frequency excitation amplitude is very low, so that the tip and sample remain in contact at all times, unlike other modes such as AC or tapping mode. I'd like to make some comments about the kind of cantilevers that we use in contact resonance. First, it's important to use rectangular cantilevers like those shown in the upper 2 SEM images. As you'll see later, our analysis model assumes a perfect or idealized rectangular geometry. So we want our real cantilevers to match that geometry as closely as possible. Therefore, we don't use triangular cantilevers or or ones with very long pointed regions like those shown in the bottom two images. Also, we have to think about the spring constant KL of our cantilever, and that depends on the expected modulus of the material that we're measuring. For materials with a modulus in the 1 to 10 gigapascal range, like some polymers, we typically use cantilevers with a spring constant of about 2 newtons per meter. As the modulus of the material increases, we want to increase our spring constant in order to for better compliance matching, so that by the time we get to stiff materials with modulus greater than about 50 gigapascals, we typically use cantilevers in the 40 to 50 newton per meter range. The basic experimental apparatus to implement these ideas is pretty simple. In the past, research groups have built their own setups by writing custom software to integrate standard lab equipment with a commercial AFM. However, contact resonance capabilities are now provided as part of some commercial instruments, for example, those by Asylum Research. The contact resonances are excited with a piezoelectric actuator either beneath the sample or in the cantilever holder. The actuator is driven by a sinusoidal voltage from a function generator. It's also possible, although fairly uncommon, to use a self-actuated cantilever. We use lock-in detection techniques on the AFM photodiode signal to find the vibration amplitude of the cantilever at the excitation frequency. By ramping the excitation frequency, we can sweep out the spectrum of the contact resonance peak. Shown here are contact resonance spectra for the 2 lowest flexural eigenmodes of a cantilever with spring constant of about 40 newtons per meter. It's important to note the frequencies. I think they may be a little higher than most people are used to working with, typically in the hundreds of kilohertz to megahertz range. Once we've acquired the contact resonance spectra and know the contact resonance frequencies, we analyze them in the following way. First, we use an Euler-Bernoulli beam dynamics model to relate the frequencies to the tip-sample coupling. In the simplest case, the coupling is purely elastic and is represented by a spring of stiffness K, the contact stiffness. Now, the Euler-Bernoulli model assumes that the cantilever has a constant cross-section throughout, and that is why we want to use rectangular cantilevers. From this model, we obtain values for alpha, the contact stiffness normalized by the cantilever spring constant. We then use a model for the tip sample contact mechanics to relate alpha to the sample's mechanical properties. Typically, we use Hertzian contact between a hemispherical tip and a flat sample. In the contact mechanics model, we need to know other quantities such as the applied force or the tip sample contact radius A. These properties can be very difficult to measure with sufficient accuracy at these scales. So instead, we rely on a calibration approach in which we make measurements on a second material, a calibration material of known elastic modulus, and we make these measurements at the same time as we make the measurements on the test material with the same cantilever and the same applied force. In doing this, we can then take the ratio of alpha values, the contact stiffness ratios, and determine values for the indentation modulus M of the material. M is also called the plane strain modulus and is related to the Young's modulus E and Poisson ratio nu of the material in this way for an isotropic material. Here are some modulus measurements made with contact resonance. The bar chart shows measurements made on a series of thin supported films. You can see that the film thickness ranged from a few hundred nanometers to a few micrometers, and the film modulus ranged from about 50 gigapascals for a fluorinated silica glass to over 200 gigapascals for a nanocrystalline nickel film. The contact resonance results agree well with data on the same samples that were obtained by other techniques, namely nanoindentation in blue and surface acoustic wave spectroscopy in purple, in spite of the fact that these techniques probe much bigger length scales. Results like these helped us gain confidence in our contact resonance techniques for making accurate quantitative modulus measurements. The table on the bottom shows modulus values for a tin oxide nanobelt. Here we place the AFM tip on top of the nanobelt and directly measured the modulus. The contact resonance value, 154 gigapascals, was much lower than that predicted by the bulk elastic constants, 358 gigapascals. However, it was very close to that obtained by another AFM method on the same nanobelt, 151 gigapascals. Therefore, we believe that the discrepancy is indicative of size effects. This example shows how contact resonance methods allow us to measure nanomaterials that simply can't be accessed with other modulus measurement techniques. So far, I've only talked about making contact resonance measurements while the chip is stationary at a single point on the sample. However, we really want to exploit the scanning capabilities of the AFM instrument so that we can obtain images of the spatial distribution in elastic properties. A simple way to do this is to keep the excitation frequency of the actuator constant near the contact resonant frequency and scan, and while we scan, monitor the lock-in detected amplitude signal. As the tip moves across regions of different modulus, the detected amplitude will change in response to shifts in the contact resonance frequency. Here are examples of this so-called CR Amplitude imaging mode. The black and white topography image shows that our sample contains a blanket film of silica, SiO2, shown in black, with a modulus of about 75 gigapascals in bulk form, and on top of that, a pattern film of niobium, shown in white, and that has an expected modulus of about 125 gigapascals based on bulk values. The pink images show the contact resonance amplitude images at two different excitation frequencies. You can see that they clearly distinguish regions of different modulus, but that the contrast in modulus, or the elastic contrast, changes depending on the excitation frequency. We can understand this contrast inversion better by looking at contact resonance spectra for the different constituent materials as shown in the upper right. You can see that depending on the excitation frequency, the peaks are shifting in different places, and so we would get different contrast. So all of this tells us that although it's very simple to obtain CR amplitude images, their quantitative interpretation is very difficult, and therefore we mostly rely on them for qualitative information. And you can imagine that if we have more than two materials, this interpretation gets even more difficult. To obtain quantitative modulus images with contact resonance, we need to acquire the contact resonance frequency at each point in the image. I'd like to introduce this term, contact resonance force microscopy, or CR-FM, as a general name for this contact resonance frequency mapping mode. On the right, in the diagrams, I've shown a couple of different ways that we could do CR-FM. On the top is maybe the most obvious, where we just do point mapping. We go into contact at each image pixel, acquire the complete contact resonance spectrum, go out of contact, and move to the next point. This has some advantages in that it's fairly easy to implement and also can be good for fragile samples. However, I think you'll find that it often takes several hours to acquire a single image, especially when you want many, many pixels. In order to achieve practical imaging rates, we usually have to rapidly detect the contact resonance frequency as we scan in contact. In the past, this required that people build their own custom hardware and software to measure and track that contact resonance frequency. However, these days, some commercial AFMs do offer CR-FM capabilities internally. For instance, Asylum Research's DART technique. On the bottom, I've shown an example of CR-FM for that same SiO2 niobium sample shown on the previous slide. The yellow images are contact resonance frequency images for the two lowest flexural modes of the cantilever. From these frequency maps, with some calibration data, we obtain the modulus map shown on the lower right in blue. And looking at the modulus map, we can now see that the value for the niobium film is higher than that of the SiO2 film, and also is about the same or consistent with bulk values. the point is not what the values of the niobium film are, but rather that we can assign numbers now to our color scale. So we actually have a way of quantitative modulus imaging. So contact resonance techniques like the ones I've just described have been used to characterize the mechanical properties of a wide range of materials and systems. The examples shown here are our own results, and they include composites and composite interphases, buried nanoparticles, and stiff biomaterials such as bone and plants. I don't really have time to go over all the material science for each image. The main point I'm really trying to make, though, is that contact resonance techniques can be applied to a wide range of materials, to polymers, metals, ceramics, and so on, with a wide range of modulus from about maybe 1 gigapascal to over 200 gigapascals, and also a wide range of material types, including bulk sample surfaces, thin films, micro and nanoscale devices or integrated devices, and nanomaterials such as nanotubes, wires, and rods.
Thanks, Donna. If you're interested in the history of this technique, contact resonance, the earliest pioneers were the Yamanaka and Arnold groups in Japan and Germany, respectively, back in 1994. These papers are definitely worth reading. As Donna mentioned, there are many ways to get quantitative information regarding the resonant frequency and quality factor. Some methods are what we refer to as point by point, and some acquire the information while the tip is continuously scanning relative to the sample. One of the most direct methods is to simply chirp the actuator with a ramped waveform, ramped in frequency space. This method provides a resonance curve that can be fitted to get the resonant frequency and Q factor. This method can suffer a bit from speed issues, and then it may take a while to acquire an image, but is very straightforward and produces nice results. Sort of tried to indicate that here with this frequency that changes as a function of time. Steve and Jesse and collaborators at Oak Ridge came up with an elegant solution to some of the speed issues, as well as some other things, with a technique called band excitation. Band excitation excites all the frequencies simultaneously in a band, frequency band, and then measures them. This improves the speed response while having many of the advantages of the chirp method. Another relatively fast method is called dual AC resonance tracking, or DART. In this method, the resonance is tracked by driving the cantilever at two frequencies, one above and one below the resonance, and then using the measured amplitude responses, specifically the difference between the two amplitudes, as an error signal to track the changing resonant frequencies. All three of these methods work well, and you can read about them in the references I've given here. In the upcoming slides, I'm going to focus on DART, the dual AC method, since it is relatively fast and simple to implement. This schematic shows the setup for dual AC resonance tracking, or DART operation. The cantilever is driven with the sum of two frequencies, a sine wave that is below the resonant frequency and a sine wave F2 that is above. So F1 is below, F2 is above. Those two signals are summed together, and then they go through an amplifier. Now, this technique was originally developed for piezo response force microscopy, where you connect to the electrical cantilever that then induces electromechanical interactions in the sample. For contact resonance, we instead go to an actuator that actually shakes the sample up and down. This shaking results in a cantilever deflection, which is measured, and indeed it looks like this. There's sort of a beat frequency because we're summing two sine waves that are fairly close in frequency together. That signal goes to two lock-in amplifiers, which analyze it and get out to an amplitude 1 and phase 1 that's measured at F1, and an amplitude 2 and a phase 2 that's measured at F2. Now, why do we have, or what can we do with these signals? Well, let's look at the resonance curve of a typical sort of contact resonance. If this solid curve here is the contact resonance that we tune on the surface, we choose F1 to be below, F2 above, and that results in an amplitude A1 and A2. And we choose those frequencies such that A1 and A2 are more or less the same. So the difference is about 0. Now as the resonant frequency changes, the relationship between those two amplitudes will also change. In this case, if we let the resonant frequency decrease a little bit, so the contact is softening a bit, then A1 increases while A2 decreases. So that means that we can use the difference between these two amplitudes, in other words, A2 minus A1, as an input into a feedback loop that controls these two frequencies. So this A2 minus A1 is an error signal that goes into a feedback loop that then changes F1 and F2 together to always keep that resonance right in between F2 and F1. What we get out of that then is an estimation, a measurement of the contact resonance. As we'll discuss in the next slide, you can also use that to calculate other quantities about the resonance, most notably the quality factor. In the previous slide, I showed you how DART uses two frequencies to measure or to follow the resonant frequency as A1 and A2. These observables change as that frequency moves around. Anil Ganapalli also figured out how to use phase 2 and phase 1 to calculate this quality factor. Now the quality factor is a measure of the tip sample dissipation. Donna will talk about that in a little bit further down, but I wanted to just give you this reference, so if you're curious about it, you can read about how to derive this from these DART measurements. Okay, we've looked at a few different methods, DART in particular, but methods for calculating or for measuring the resonant frequency in contact resonance. It'd be nice now to step back a little bit and look at the noise estimations for this. So what I mean by noise estimates is that if you measure a resonant frequency, and that's our step 1, measuring observables, as I discussed before, if there's an uncertainty in that measured contact resonance, how does that translate into either a stiffness or a modulus uncertainty? And so in general, we expect that we should be able to measure the uncertainties to within 1% or less, depending on the resonant mode and the frequency and so on. And the conclusion that I'm going to demonstrate here, or at least to discuss a little bit further, is that you can expect that to lead in turn to 5 to 10% uncertainty. Well, 5%, maybe sometimes if you want to be conservative, 10% uncertainty in the contact stiffness. Now Donna chose some examples here. The first one she chose was a compliant material with a modulus of about 4 gigapascal. And this is a relatively stiff polymer, such as polystyrene, high-density polystyrene. If you assume using a fairly soft cantilever for this, 2 newtons per meter with 70 kilohertz free air amplitude. Now, if we assume that we can measure the contact resonance within about a kilohertz, plus or minus a kilohertz, it actually leads to about a 1% error. If our contact resonance uncertainty is more like 5 kilohertz, then we're at about 0.2, and that gets us to that 5% number. For a stiff material, now we're going up to 130 gigapascals for something like a metal like niobium, using a stiffer cantilever, of course, 40 newtons per meter with 170 kilohertz free air. We see again, if we can determine the resonant frequency to within a kilohertz, that we're less than 1% or so. And if we jump up to 5 kilohertz, the modulus uncertainty is about 4 gigapascals, so about 3%. Again, under this 5% estimate from before. I want to say a few words about actuation. If you think about it, what we're doing here is we're trying to shake our sample at, or maybe our cantilever, at minimum of 100 kilohertz up to maybe several megahertz. And if you think about it, that's actually a bit of a tough thing to do. Over the years, there have been quite a few methods that have been attempted. I'm just going to mention a couple of the most accessible. Donna also alluded to some others. The first and the sort of easiest is to just use the shake piezo. So this is number one up here. The shake piezo that is used to do modes like tapping or other types of AC modulation in your AFM. I'm not going to show any data here because it actually tends to be a little bit scary, but you end up literally with what people refer to as the forest of peaks. Now, the forest of peaks was noticed many years ago in conjunction with fluid tapping, but it originates from a large range of resonances, mechanical resonances, in the construction of the AFM or its environment itself. And it comes about because piezos are actually really powerful drivers. They don't move very much, but they can exert tremendous forces. And so what they end up doing is they end up exciting many, many resonances in the mechanical structure of the AFM itself. By taking those same piezo actuators and highly damping them, we can make the situation much, much better. So I'm showing, here's an actuator that's in our MFP 3D AFM. This is a similar kind of actuator that's in our Cypher AFM. These are contact resonance sample holding actuators. You can see the cantilevers positioned above there and the samples glued directly to it. By using a damped actuator like this, you can avoid exciting many of those resonances. And really, for at least to date, this is our best and most successful solution. You can also use things like iDrive, which is a magnetic technique where I've shown it here. So you drive a current through this cantilever, this flexible cantilever. The cantilever has to have two legs, and if there's a magnetic field there'll be a Lorentz force that makes this cantilever oscillate up and down, and so you can actually drive the contact resonances here. This is, at first blush, a very attractive technique. It looks like you're basically delivering all the oscillation energy, the excitation to the cantilever. Unfortunately, as you can see, there's legs here, and there's an image here of another silicon cantilever like this. Because you're driving a current through a wire, it's like the LTA cantilevers I talked about before. The cantilever shapes tend to be very irregular, which, as Donna told you, is not very good for trying to make the measurement quantitative, and certainly getting a modulus out is very difficult. The other side of it is that you have very limited cantilever choices on this.
So far, I've only talked about how to obtain elastic property information using the contact resonance frequency. We can also obtain viscoelastic information by measuring not only the contact resonance frequency, but also the quality factor Q. If we have a narrow contact resonance peak, we have a high value of the Q factor, and this indicates low tip sample damping. If we have a broad peak, the Q factor is low, and we have higher tip sample damping. Recently, we worked with our collaborators at Asylum, ExxonMobil, and the University of Nebraska-Lincoln to demonstrate the concept of viscoelastic CR-FM. The black and white topography image shows the sample was a polymer blend containing regions of polystyrene in a surrounding matrix of polypropylene. The two middle images are the contact resonance frequency and quality factor for another section of the same sample. You can see that there's very little contrast in the frequency and much more contrast between the two materials in the Q factor map. We analyze these images using a Kelvin Voigt element, namely a damping dashpot in parallel with that elastic spring, to represent the tip sample interaction. From this, we obtain the maps of relative storage modulus E prime and relative loss modulus E double prime, shown in the bottom right. These maps are normalized to the values in the polypropylene continuous phase. you can see that there's not much difference in the elastic properties, the E prime or storage modulus, but there's much more difference in the loss modulus, the inelastic or viscoelastic term. The contact resonance results were consistent with values obtained on bulk samples of the same materials using dynamic mechanical analysis. And these measurements had been frequencies shifted up to the contact resonance frequencies using time temperature superposition techniques. Since this initial demonstration of viscoelastic CR-FM, we've also developed a new way to determine the viscoelastic loss tangent, or tan delta. With this approach, we directly calculate tan delta from the contact resonance frequency and quality factor without intermediate calculation of E prime and E double prime. Some features or benefits of this approach are that it does not require a calibration sample or calibration data in order to determine absolute values of tan delta. Also, we don't have to make assumptions about the specific tip shape or assume that it's an idealized shape. In our initial work on several polymer samples with this method, the CR results for tan delta compare favorably with values obtained by DMA and nanoindentation. These measurements were made on materials with tan delta in the range from about 0.02 to 0.2. So we're encouraged by the potential of this method for viscoelastic characterization in a range of systems, some of which I've shown here, such as the polypropylene polystyrene blend, a composite interphase region, and the bone cartilage interface on the right.
Thanks for that, Donna. In the next few slides, I'm going to show you a few examples of viscoelastic imaging with contact resonance. We'll look at a polymer blend, a metal polymer PC board, and then finally we'll look at localized thermal measurements using small heated cantilevers. The first example I'm going to show you is a polypropylene polystyrene blend that was produced by our friends Dalia Yablon and Andy So at ExxonMobil Corporate Strategic Research. This sample was microcryotome, as you can see here in the topography. There's the polypropylene and the polystyrene inclusions. You can see the knife marks in the polystyrene. If you look at this, here's the quality factor and resonant frequency mapped using DART. And the one thing you can notice immediately is that the resonant frequency map is actually quite close between the two materials. And we actually expect that because the moduli of these two materials are also, the elastic moduli are actually quite close. What is interesting is that in the quality factor image, there's a big difference. And what is nice about these results is that the polystyrene is expected to be much less dissipative than the polypropylene. The second example is a copper PC board junction that was sectioned. This sample came from our friends Dr. Han, at the Korean Institute of Standards and Technology. The image here shows you the rendered topography. You can see some structure in it. It's been polished. It's been cryotomed and polished. I'm going to now, on top of this topography, show you the resonant frequency, and this was measured with DART. You can see in this resonant frequency image that the copper, shown here in bright, is very, very clear. That has a frequency close to a megahertz. It's 900, and on the label here, 900 and some kilohertz. Whereas the PC board, the soft polymer in the PC board is on this side, and that is a considerably smaller resonant frequency over that material. Now note that this range is very nearly 200 kilohertz, so there's a very big mechanical change in mechanical properties as you go over these two materials. There's also an interesting little inclusion here, which is some sort of, well, we don't know what it is, some sort of impurity or something else that's sort of in between these two materials, sort of about 850 kilohertz. We can now, on top of this, also overlay the quality factor, Q. Now, the higher the quality factor, the less the dissipation. The lower the quality factor, the more the dissipation. And you can see this is all sort of consistent with the copper. The dissipation over the copper, since the Q is high, is very low. And the dissipation over the polymer is high, and therefore the quality factor that the cantilever measures is lower there. This little inclusion shows sort of intermediate properties there as well, somewhere between the copper and the PC board, so quality factors that are somewhere in between. The final example I'm going to show you for using contact resonance is a slightly different application. This isn't an imaging application per se, but rather a localized measurement of mechanical properties while the tip is heated. And to do this heating, we're using these special little cantilevers that have built-in resistive heaters. This came out of the work from Bill King's lab at UIUC. You can read about it in these references here. The idea is you run a current through this cantilever with two legs, and there's a resistive bit here, and as the current flows through, the tip warms up. It gets very, very hot in some cases. You can use this in a variety of ways. You can make just localized little deflection measurements as you heat it up. Here's an example here before and after. This is a SEBS polymer where we've induced a localized phase transition in a couple places. What we've done is we've combined this with the high sensitivity of contact resonance to make simultaneous high sensitivity mechanical measurements at higher temperatures, localized higher temperatures. And we were very proud a couple of years ago to win an R&D 100 award for this work. These are insulin fibers on a mica surface. Now this is just the topography image, and these little marks here, these little crosses, circles with crosses in, are places that we put the cantilever down. We actually did an array of point measurements here where we put this cantilever down on the surface and then ramped the temperature up as we measured both the deflection, the contact resonance, and the quality factor. So these are the color-coded results above these areas. So here's the yellow. That's this little curve right here in the contact resonance. The first thing you should notice is that the deflection was changing a little bit because of the bending from the cantilever. There's basically nothing noticeable as you ramp the temperature up versus time. The contact resonance, on the other hand, if we're here over the bare mica, it stays more or less constant. But as we look at the curves that are over these insulin fiber molecules, we see big changes in that. Now if we look at the same, I should mention that we estimate this temperature to be about 85 degrees Celsius. If we look at the image after this heating experiment, we see that at these locations where we see this shift in the resonant frequency, we see that we've indeed done something kind of dastardly and terrible to the insulin fibers. We've somehow thermally decomposed them. Over the mica, where there is no insulin, nothing changes. These red, the blue, and the purple curves remain more or less constant. Now the takeaway message from this is that at the same time we're looking at the cantilever deflection, which is analogous to a force measurement, a force curve measurement, and in that case there's just nothing that happens here. It's only in the contact resonance that's so much more sensitive that we see this jump in the behavior. Okay, with that, I'm going to wrap up this webinar presentation. I hope we've convinced you that contact resonance is an emerging technique that can provide you a lot of interesting, both qualitative and quantitative data on the mechanical properties of a lot of materials. It's good in that it's and rather unique in that it ranges from a gigapascal to 200 to 300 gigapascal. And it can be fast. It can be used while scanning to make nice mechanical maps. That it will help us as we move into the future with the characterization of a wide range of materials and devices. If you would like to go further in this and learn more, first of all, there's a lot of references in this presentation. I'd encourage you to consider attending a nanomechanics class here that we hold at Asylum Research in Santa Barbara, California. You can also visit us at these upcoming events where there will be application scientists that could tell you more about these capabilities. Finally, last but certainly not least, I need to acknowledge all the people that have helped with this. Donna Hurley, who you heard from today, and Jason Kilgore at NIST, Ryan Wagner and Arvind Raman at Purdue, Stephen Jesse, Brian Rodriguez, Maxime Nikiforov, and Sergei Kalinin, Walter Arnold, who has provided many helpful suggestions over the years, and also thank you for giving me the Band-Aid for my cut at the last conference we met, Dalia Yablon and Anzi Tso at ExxonMobil Corporate Strategic Research. And finally, here at Asylum Research, there's been help from a ton of people, but especially Anil Ganapalli, who developed a lot of the techniques that you saw today, and Clint Callahan and Jason Bemis, who have implemented so much of this stuff in the software. Thanks very much, and we're ready to take questions now.
Okay, thanks a lot, Roger, and thank you, Donna. We do have some questions that we'd like to cover. Before we get to that, though, I just want to reiterate that the recording today is going to be available. First of all, you'll be able to follow the link in the registration email that you got, the same one that you followed to get here today. If you follow that after the webinar, you'll go to a recording of it where you can view it. And again, it'll also be archived on our webpage as well, which is www.asylumresearch.com/webinars. So we have several questions. The first one will go to Donna. The question, Donna, is what is the effect of roughness on contact resonance measurements?
Thanks, Ben. That's a really good question. As with any contact technique, our signal in contact resonance is also sensitive to the contact area between the tip and the sample. So roughness definitely does affect the signal. I think you could see that in some of the images I showed with a more textured film had a lot more kind of graininess or scatter in the data. So if you have a very, if your surface roughness is smaller than your tip contact area, you will see some of that. But for now, I think that's about all we can do, and we work with it and take averages of the average properties of the material.
All right, thank you. The next question is for Roger then. The question is, what is the difference between force curve measurements and nano-indentation measurements?
Thanks, Ben. That question actually comes up a fair amount. Probably the biggest difference is with cantilever-based indentation measurements, force curves. The cantilever, when it is pressed into the surface, because it's at an angle with the surface, it actually ends up sliding a bit across the surface, and that's actually very difficult to quantify. In the case of indentation, it's vertically oriented, and it's that axis is very well defined, so we don't get a lot of sliding motion, which makes it easier to quantify. Also, typically the indentation depths for an indenter are quite a bit larger, which tends to make the results more quantitative.
All right, thank you. And next, a question for Donna. So back to contact resonance. The question is, this is all carried out in the linear regime, but how does one account for tip damage? I believe this should affect the modulus measurement too.
Yes, that's right. This is actually related to the earlier question I answered. It's the same idea that we do have to our signal does depend on the tip sample contact area. So especially when we're working with very stiff materials like metals or ceramics or very hard materials, the tip will wear, and we have to be aware of that. And so your signal might be gradually changing, and this is a reason for using the calibration approach. If you want quantitative modulus measurements, then with the calibration approach, we compare measurements made on the unknown material to the calibration material constantly in alternation, and so it's sort of the best way we have right now for compensating for the tip wear. And we've actually used we've actually shown how you could turn this around and use contact resonance signals to monitor tip wear in much more real time than you could with other techniques. But until we have a perfect tip that does not wear, this is about the best we can do.
All right, that's great. Thank you. So another question then about possible artifacts. Roger, you can take this one. Are there significant edge effects as well, and how would you measure the modulus of objects in the 10 to 50 nanometer size range?
That's a good question. This is This is actually related very closely to what Donna was talking about, surface roughness and so on. I guess I tend to think of this in terms of that three-step model we discussed, and really this comes down to step 3. So with small objects that are 10 to 50 nanometers, the Hertz contact is no longer valid, and you have to think about other kinds of models. Now, there's a lot of different things out there. One I just learned about recently that you might want to look at is the so-called Tatara model. I think it's T-A-R-T-A-R-A. And in that model, basically, it's like a Hertz model, but in the limit where the tip itself is much larger than the object you're trying to measure.
All right, thanks. Donna, then, a question about composite materials. So, for example, carbon fibers in a polymer matrix. In a case like that, what kind of cantilever would you choose?
Yes, that's a really interesting and complicated question, but I'll try to summarize the way we think about it now. We didn't really talk much in the seminar about this, but by choosing different flexural modes of the cantilever, you can address different regions of contact stiffness. And so instead of maybe thinking about it in terms of cantilever stiffness directly, you can think about it in terms of using one cantilever with different modes. So one option we're trying to work towards is the idea of using the same cantilever with different flexural modes to be sensitive to both more compliant and stiffer regions. When we've been working with the composite materials we've worked with, typically the matrix might be in the 3 to 5 gigapascal range of polymer, and the fibers might be anywhere from maybe 10 to 100 gigapascals. And we usually start with a cantilever of about one that matches the matrix better, maybe 2 to 3 newtons per meter, and then use the second or third flexural modes to get increased sensitivity. But that's all. I guess what I'm trying to say is it's kind of a new way to think about contact resonance, or a new application of contact resonance. So I don't really have a great pat answer for you.
All right, thank you. Roger, then, a question. How do you glue the sample to the actuator, and isn't the amplitude too low for very stiff materials? And then an additional question about damping of the actuator. Can you just add a very heavy mass to the actuator to eliminate this forest of peaks effect?
So this is an interesting question in that I view the design of these actuators as a little bit of a black art, in that you want the sample to move as the questioner asked, but you need to have it be a really flat function of frequency. The glue, we've tried several different kinds. The one we've settled on is a 5-minute epoxy. That's a nice combination of sort of usability and coupling the acoustic energy well to the sample. Some people think you can use honey, other kinds of liquids like that. I haven't actually tried that, but you could do that. As far as the design of the actuator, the damping is important. Adding a mass might work, but I think in that case, all that may do is reduce the frequency response. And as you remember, we want to be able to drive this thing up at maybe a couple megahertz. And so the heavier the actuator is, the harder it is to drive up at those high frequencies.
Okay, thanks, Roger. Don, a question about the range of the technique. In the presentation, a lower limit of about 1 gigapascal was referenced. What sets that limit?
That's a good question, and is sort of indicative of the state of the art. This technique, as you've seen, was really, when it was first developed in the late 90s by groups in Japan and Germany and elsewhere, it was really intended to address the higher end of the modulus range, the stiff range, because there really weren't a lot of other techniques that could do that. In my own group's work and other places, people have been trying to drive that down because of all the interest in nanomechanical properties of polymers. So right now, we've kind of extended the technique so that we feel comfortable about our methods for getting good numbers in the few gigapascal range. What limits going even further are things like taking into account adhesion forces and other and viscoelastic effects in the much more compliant polymers. So we'd like to go to even lower materials, but that is a state of active research and will involve more complicated contact mechanics models and kind of refined measurement methods.
All right, thank you, Donna. So we're coming up on the end of our allotted time, so we're just going to take one more question. If we haven't gotten to your question yet, though, be sure that we will get back to you offline then, individually, with an answer. So the last question will go to you, Roger, and that is, these contact resonance techniques, are they available on the Asylum MFP3D, or does it take additional hardware to do these techniques?
The software for both surface chirps, of the sort that Donna talked about, and for DART are available sort of as stock software packages. Band excitation is a separate module. And then the actuators themselves, of course, are additional. And they're available both on the MFP3D and on Cypher.
All right, well, I'd like to thank everyone again for attending the webinar, especially thank Roger and Donna for presenting. And again, remind everyone to check our website for future webinars, as well as look for the recording of this webinar to be there very shortly. Thank you very much.